Okay, so today is the session number 19 of the second semester on braided fusion category. Last week we proved this lemma, this proposition, in fact. Yeah. So it was a proposition about the most attracting that you can reformulate the non-degeneracy of D. So recall that D is a braided fusion category containing a Tanakian category E. And then you can apply the disequivalentization, which is called C, and you consider the neutral component of the G grading. Remember that DC is a braided G cross fusion category, so it has a G braiding, a G grading, and G braiding. I forgot. It's something else. And so the neutral component for this grading is non-degenerate. This is a fusion this is a braided. Is non-degenerate if only if D is non-degenerate. And there is so you can see this neutral component has the disequivalentization of the Muger centralizer of the Tanakian category. Yeah, here, be careful. And you can see also the fusion subcategory generated by the Muger centralizer of the NE is equivalentization of the Muger centralizer of C1 in C1, and also something involving the grading. Yeah. So this is what we did. Yes, we finished by that last week. So now we talk about Lagrangian category. So recall the following definition. On the introduction. But we already defined Lagrangian introduction. So remember that the Lagrangian category is as follows. Let D be a braided fusion category. Tanakian subcategory in D is called Lagrangian if it is equal to its Muger centralizer. And the following proposition provide equivalent reformulation for Lagrangian subcategory. Following condition. prendre le Tanakian subcatégorie. R equivalent. So first, E is Lagrangian. So this is equivalent to what? Equivalent just taking the neutral component of the disequivalentization of D to be trivial. And which is also equivalent to the fact that C is pointed and the cardinal of every component for the grading is of simple object in the grading are at most one. Okay. So proof. So from the previous proposition, I just recall at the beginning. From proposition 456, first point. Then the above point 1 and point 2 are equivalent. Okay, so let's come back to this first point. So this is this one. Yeah, so let me just copy and paste this. I will delete it, but just then we can see at the same time what we have to prove and what we know. So we have that this is known, and we want to show that 1 equivalent to 2. So assume 1 is true. So you have E to be a Tanakian subcategory of D equal to its Muger centralizer. So that. And we want to show that. So because it is equal to its Muger centralizer, you have, so this E prime is equal to E. But the, the condensation of E by E is trivial. So you directly get that this, because here you can remove the prime. So this is okay. Now, if you assume that, then this is Vec. So here you have Vec power G, which is E. So you have I prime equal E. So this is immediate. So let me write OK. You can, if you like, you can write an exercise, but I just, yeah. I just explained. So it's, yeah. No, I don't need to write exercise, it's just OK. Okay, now there is another aspect which is also immediate. It is also clear that 3 imply 2. Why? Because in 3, C is pointed and every component is at most 1. We know that the number of simple objects is at most 1. We know that the neutral component is at least 1, so it should be exactly 1. So but the neutral component contain vec, so it should be exactly vec. So 3 imply 2, which is also trivially okay. So then we just have to prove 2 imply 3. Now, assume to hold. Now we want to show 3. So first, take, so what is 3? So we want to show that every object in C is invertible first, which means C is pointing. So you take every simple object in C, invertible. So you take a simple object in C. So for every simple X in C, so the object why I wrote this way? Okay. The object X tensor right dual of X. I don't know why I want to write this way. Right dual of X. Let me check. I guess you can prove the same thing with the left dual, but it does not matter. It's the fusion category. You have left and right dual, but it's useless. Uh, why do I want? I don't. Let's write with the right dual, but I guess you can write with the left dual also. So then this object lie in the neutral component, which is vec. So remember that the dual, left or right, in fact, if you have an object which is in this component, the dual is in the inverse component. So when you multiply the two, they are in the neutral component. I'm not mistaken. Yeah. Yeah, it should be. Yeah. So it is in the neutral component, which is vec. So this one. This is a multiple. This is a unit object with some multiplicity. But so let me write just that. X in CG only if the right dual is in CG inverse. So I guess we are using that. So I just have a little doubt whether this is true for all braiding we are considering. I guess it's for sure it's true in the modular case. For any braided, in fact, C is not even braided. For any grading, is it true that the dual maps a G component to a G inverse component? So it should be true. It should be true, but I just have a little doubt. So let me write like that, but it should be true. Okay, so you have that. Then, but here you can apply also the, so on the other hand, dimension of the home space extensor path. This is equal to the dimension of xx, which is equal to 1 because x is simple, sur le map. And this is called the, I forgot the name. Connectedness? No. So there is a name of this kind of isomorphism between a home space, but you can call that the
Frobenius reciprocity.
You can call that the Frobenius reciprocity. But in EGNO book, there is another name. Frobenius reciprocity, natural adjunction isomorphism. Frobenius reciprocity or natural adjunction isomorphism. And for natural adjunction isomorphism, you can apply right or left dual. So maybe you need to put the left dual here, but it's okay. There is no need to write the right dual, but anyway. Anyway, so this is equal to 1. So the multiplicity of the simple object here is 1. So this is just equal to 1. And so x is invertible. So x answer right dual of x is isomorphism isomorphic to 1. Meaning that so every simple x in C is invertible. Let me check something. Anyway. Okay, so C is pointed. So we have the first part. Now we have to show that every component has at most one simple object up to isomorphism. And is pointed. And so this is a group. So this is important. We will use that it is a group. So now by 2, the grading homomorphism from this group to this group has trivial kernel by definition. What is the kernel? The kernel is the simple object which are in the trivial component, but there are only the trivial object. So the kernel is trivial, so there is a trivial kernel. By yeah. So it's trivial. Okay. So this map, this homomorphism is injective. So it is injective. Injective mean what? Mean that for all. So if you have two different simple objects, they will map to two different group elements, which means that two different simple objects has different degree in this grading, which exactly mean that. Injective. So, where is it? Therefore, this is at most one for all G in G. In other words, so 2 implies 3. So let me repeat what I did not wrote here. The kernel are just the set of simple objects here, but this is only the unit, so the kernel is trivial. This is a group homomorphism with trivial kernel, so it's injective. Injective mean that two different simple objects map to two different elements of the group, so two different degree. So you cannot have two simple objects with the same degree. So it's almost one. Of course, you can have an element here which is not the image of anything, so it can be 0 also here, but it's almost one, at most one. Okay, so it was not complicated. Okay. And here is an immediate corollary of this proposition. The next result follow immediately from the previous proposition. And the previous proposition point to the point involving the non-degeneracy. So corollary 459. So the following conditions are equivalent. So one, D, so D is still braided fusion category, and E, a Tanakian subcategory. So D is non-degenerate, and E in D is Lagrangian, if and only if C is pointed and the grading is bijective. The grading map from that to that is bijective. So this is immediate, but let me explain a little details. So what about that? Okay. So this implication. So you assume D is non-degenerate and E is Lagrangian. So we know E is Lagrangian. So we know so so because it is so you have D is non-degenerate. So D non-degenerate, you have the grading is faithful. D is non-degenerate, so you get the faithfulness of the grading. And E is Lagrangian, is that you have this. So you have injective grading. So a faithful injective grading is bijective. So, yeah. So the non-degenerate imply faithful grading. Et Lagrangian imply injective grading. So together, it's a bijective grading. Okay, and what about the other way? So here, faithful grading means the grading map is surjective. And the other way, so you assume that C is pointed and the grading is bijective. So this grading map is bijective. This implies that C1 is vague. And faithful grading. Bijective, so in particular faithful grading. But C1 vague and faithful grading so C1 vec imply D is vec. So wait, let me come back here. C1 vec is it mean non-degenerate and faithful grading. So we have the two, so which is equivalent to D non-degenerate. So you have D non-degenerate. So imply D non-degenerate. And then why it is Lagrangian? C1 is vec, so it's okay. So this directly implies Lagrangian. Imply Lagrange. Okay. So and here you use cat force is 2. And here it's just proposition for okay. Okay. So next. Talk about pointed category as braided G cross category. Pointed category as braided G crossed category. Hmm. Okay. So this remark, the coming remark is a little, how to say? A little too much, maybe. Maybe, I don't know if you say in English, it's an overkill. So, in the sense that you want to kill a fly with a tank or something like that. You don't need this kind of details for such a straightforward statement, but anyway, that's maybe there is a reason I am not seeing. So let's write how they want. So let A be a monoidal category. Every invertible object X in A determine a monoidal equivalence add X from A to A. And so add X of Y is X tensor Y tensor X inverse, but in fact you should write X dual because invertible means the dual is inverse. So yeah, usually you write dual, you don't write inverse. So here invertible means, because we are in monoidal category, with a left dual X star defined with evaluation and co-evaluation map, so with zigzag relation, such that evaluation and co-evaluation map are isomorphism. So in other words, X inverse equal X star. Because remember, evaluation map, co-evaluation map are from X star tensor X to 1 or from 1 to X tensor X star, or maybe the star is there or there, I forgot that. Yeah. Anyway. You can write inverse, you can write dual. My opinion is maybe better to write dual, but anyway. So if mod A is k-linear and the endomorphism space of the unit is one-dimensional, then for every invertible object X in A, the homomorphism from the non-zero scalar, which is just the automorphism group of the simple object. The invertible implies simple. X, because the invertible is simple, because the unit is simple. 2. O is trivial. And trivial means image is 1. The homomorphism is trivial. Image equal the trivial subgroup. And Y, moreover, if moreover 1, what happened? In fact, you have X tensor something tensor X inverse make vanishing. So the constant vanish. So vanish is for 0, here is 1. So make the constant cancelled. Constant cancel. Make. Anyway. So it's trivial. So, which mean that this so this is the overkill is there. They are just saying that in fact, then this depend only on the isomorphism class of X. Depend up to a unique isomorphism only on the isomorphism class of X. So all this paragraph just for that. I guess that in a lot of place in this paper, they wrote more complicated statement without any justification. And here, this long justification for something more or less trivial. Okay. Thus, so maybe I am missing something. Maybe it's not trivial, but the group of isomorphism class of invertible object of A act on the monoidal category A. So just to see that this induce an action of the invertible object to A. Up to isomorphism. Yeah, okay. I guess my opinion for this paper, I just need to write. It's trivial to say that this induces an action up to isomorphism. There is no need to write and to go to the monoidal category also, which is crazy. We are dealing with fusion category. What's the point of? I don't know. So kind of overkill. Maybe because they will use that in the appendix because In the appendix, they are dealing with some generalization, so maybe they need that for something else, but for our need, it's not required. In fact, maybe this is the same also for the right dual here. Because in the fusion category, there is no, maybe this may be useful for something more general, maybe. Okay. So that's for this remark. So now, let's see, be a pointed fusion category. And let G be the simple object of two isomorphism, so they are all invertible, this from a group. Then so as I said, every simple object of C is invertible by definition. So G is a group. By the previous remark, G acts on C via conjugation. G map to. Maybe I have an idea why I wrote this remark. I guess it looked like initially they did not write anything. I just write that, but maybe the referee of the paper say, I want more details about that, so they added this remark. That's why it's overkill. It's a joke in some sense it's a joke for the referee. Okay, so via conjugation. Okay. On the other hand, C. So C, what is C? Yeah, it's a pointed. So C carries the canonical G grading. Given by the fact that C is a kind of so by G, in fact, it's a simple object. So just the identity map. So the identity of that. So we identify the two. So this is just the equality as a grading. So you have this grading. So after the pause, we will explain why this G grading and G braiding. G grading, G braiding, G action. You have three G things. So we claim that the G action and the G grading can be combined into the structure of a braided G cross category. Of a braided G crossed category. The precise result will be after the pause. In fact, the way it is written here is a little bit false. in the sense that you expect that you will start from this G action and G grading, and you will make a G braiding satisfying all the axiom of a braided G cross category. But in fact, we will not do that. The proof will start from one of the two, I forgot. And we will consider the axiom of, and then you will, I guess you will come back. I guess this one, yeah, you will see this one, there is no choice. So we'll just start on one of the two and show that there is no choice but to get the other one. Anyway, pause. Okay, so here is a precise statement. Proposition 461. The canonical G grading on C can be upgraded. So we see there are different levels of preciseness upgraded to. So we will explain later what we mean exactly by upgraded to upgraded G cross category structure on C. This upgrade is unique up to a unique isomorphism. Up to unique isomorphism. This is the first point. Second point. The resulting G action. So as I said, you start from the G grading. This only the G grading, and it can be upgraded into a braided G cross category structure in which the G action is the action by conjugation. Yeah. So you don't start from the G action and the G grading, you just start from the G grading and you recover this G action to satisfy all the property of a braided G cross category. So it's not resulting, it should be the corresponding because it's not a resultant. The corresponding G action on C is the conjugation action. And yeah, and the last point. So remember that from a braided G cross category, you can associate its equivalentization, which is a true braided. So here you start from the pointed, which is not braided. So it has a structure of braided G cross, but it's not braided. Particular, even if G can be non-abelian, so the quadratic ring of a pointed may not be commutative. So what is a braided structure associated to that? In fact, it's the derived center. So the braided fusion category. So the equivalentization of C. Associated with the braided G cross category C identify with its Seinfeld center. Canonically with the Seinfeld center more precisely. The braided functor from the equivalentization to the Seinfeld center from remark 443.1, so I forgot what was this remark, is an equivalence. So let me check. What was this remark? It was a remark about the braiding-like structure, G braiding structure. Yeah, the G braiding structure. So isomorphism from X tensor Y to Y tensor X, where Y is equivariant and X is in C. Define a braided functor from the equivalentization of C to the Seinfeld center with composition with the forgetful functor equals the forgetful functor from CG to C. Something like that. Anyway. So we have a forgetful functor from CG to C. So if you compose, it can be obtained by this and the forgetful functor here. So this is the forgetful functor from CG to C. This is what this remark is saying. And so this functor in this remark is in fact an equivalence. So these are identified with the triple center. So before the proof, there will be a remark. Remark 462. So in one, yeah, it's about upgrade. To upgrade mean to define an action G on C together with a functorial family of isomorphism involved in the definition of braided G cross. So it was called AT. So it was the G braiding, something like that. Satisfying condition A to D of definition 441, which is the definition of braided G cross fusion category. Fusion category. All such upgrade. So this upgrade, so define an action together with functorial family satisfying A to D. So all such upgrade form the set of values. This collection of upgrade form a groupoid. The G action is a monoidal functor from G to the tensor functor from C to C. So there is a natural notion of isomorphism between action and hence between upgrade. There is a natural notion of isomorphism between actions and so between upgrades. Okay. Natural notion of isomorphism. Okay. Anyway, so the proof of this proposition yeah. So giving a functorial family of isomorphism, so giving as in the definition, even giving a functorial. Let me just read what was 80. So 80 was the G braiding, in fact, CXY from X tensor Y to GY tensor X, where G is in G, X is in the G component of C, and Y is in C. And it's called the G braiding isomorphism. So given a functorial family, isomorphism 80. So maybe I will write. It's quite far. So this was CXY from X tensor Y to Y GY tensor X G in G X in CG CG sorry and Y in C. Okay. So giving a functorial family of such isomorphism, For all x in CG, so giving such a family is equivalent to giving it only for invertible object x in CG. Remember that C is pointed. Wait, C is pointed, yeah. Pointed. So the simple are the invertible. So you are just saying that you can reduce to the simple. Giving a functional family for all such x is equivalent to giving that for the invertible. Okay. Now, if x in CG is invertible, then AT is equivalent to an isomorphism this way. In fact, you can move the x on the right. You will move this one here, we put it an inverse. And then you will be very close to the notion of cross product for finite. So Gy. So very close to cross product of group. Okay, so you have that, and then so in other words, you have something with adjoint map, a functorial isomorphism by G from adjoint x, adjoint Gy, it should be x of G, and wait. Wait, add G. Let me write x because it's defined from x before add G. Oh yeah, okay. Now I remember. It's defined. This is the overkill. It's only the isomorphism class. For all y, remark 460. Okay. So now, what about the hexagon-like axiom? So the commutativity of the diagram 82, which is the first hexagon-like axiom, commutativity of 82, so which is the first hexagon-like axiom, or hexagon-like, not an axiom here. Commutativity of 82 state that. So you can see that as an exercise. State that each by G is an isomorphism of tensor functor. So exercise. Just need to check. And commutativity of 83, which is a second hexagon-like. Second hexagon-like diagram. So it means, what does it mean? This one means that the collection phi G is an isomorphism between two G actions. Between the following two, between the two G actions on C. So this one and this one. So exercise. Let me check. I wrote correctly as it is written, yeah. So, so you have an isomorphism between two actions. I see. But you will see, we will say we will explain that there is, according to that, there is no choice but to take phi G to be the identity and G of Y to be the adjoint. So there is exactly one way up to a unique isomorphism to define an action Gy maps to Gy and a compatible family. By G. With these properties. The only choice, possible choice is namely G of Y equal, you take just the identity, by G equal identity. So an exercise You have to check that you have no choice but to take the identity. Okay. So then it's immediate by construction that the collection of the family of isomorphisms satisfy the condition B and D of the definition of braided crossed, and then you can deduce from B and D that it satisfies A and C. So again, it's an exercise. I'm not interested in going into such details. By construction, the resulting family 80 satisfy condition B and D. So condition B and D was the isomorphism CXY are functorial in X and Y. And D is the following. D is the two hexagon-like action. But we already, yeah, we already make the thing in such a way that by construction, in fact, we construct something in such a way that it satisfies the hexagon-like action. And B, the functoriality, so it should be related to where it should be written functorial somewhere. Functorial, yeah, should be related to that. So this is by construction, it is immediate, and then A and C deduce from B and D. So A is something involving the adjoint action, and D and C is a way. So isomorphism X, C, X, the isomorphism C, X, Y are compatible with the G action. Something like that. So by construction, you have B and D. Of definition for 41. And it is straightforward to verify that is also that it also satisfies A and C. Verify that it also satisfies A and C. Exercise. Okay. So this, from that you get 1 and 2. So this upgrade into braided G cross where the G action is the conjugation. This proof part 1 and 2. So what about part 3? Part 3 is about the Drinfeld center. So the equivalentization of C. So C is a pointed, seen as a braided crossed, and its equivalentization is its Drinfeld center. So part 3 follow directly from the definition of the Drinfeld center and what was written in section 444. Okay, so let me check. What is 444? Yeah, it's the section called equivalentization of the Yeah, so when we discussed for the first time the braided cross, we discussed about the equivalentization of that involving so the Dunfeld center was somewhere, I guess, with the central structure as a canonical structure of central functor involving the Dunfeld center, etc. And so from what is written in this section, you deduce directly that it's the definition of the Dunfeld center. Follow directly. So what was read from associated to Yeah. In fact, you are starting from that. You take the equivalentization. What is the Dunfeld center here? They are just taking the element, the object, not necessarily simple, which commute with the other object, and you take a functorial isomorphism for this commutation. And in fact, this functorial isomorphism is called half braiding, and this half braiding, you can see it's nothing but in fact the G braiding of the braided G crossed. In the equivalent case, is braided G crossed with G braiding the braiding, and you see that it is exactly the half braiding defining the Dunfeld center. So part 3 follow directly by comparing section 444 with the definition of the Dunfeld center, which is in section 2.1. And if you want, you can write more details as an exercise. Okay. So last remark before the next subsection. In the proof of the previous proposition, yeah, we see that condition A and C follow from B and D. And they are saying that the same phenomenon appear in appendix where they generalize this proposition to something more monodial or with less assumption. Well, I can almost omit this remark, but anyway, we see that conditions A and C of definition 441 follow from conditions B and D. The same phenomenon appears in proposition E16, we will not cover, which generalize proposition 461. If you insist, I will just read proposition E16. No, it's not even. There is a typo. It's not E16, it's E61. They wrote E16 in there. What? Yeah, E16 is a type. There is no proposition E16. So I don't know what they are referring to. Maybe it's a section E16. Yeah. Yeah, E16. Yeah, so it's false. Okay. So let me read that. In the case of a faithfully degraded GR category proper. Yeah, I will not read it. It's too complicated. Something with less assumption, generalization, closer to the general monoidal category. I will not read it. It's too. There are too much notion which are not defined. Okay, so let's come to the next subsection called center of pointed categories and Lagrangian subcategory. Center of pointed categories and Lagrangian subcategories. Recall. Oh, where is my line? Recall that the Drinfeld center is non-degenerate. Recall that the center of any fusion category is a non-degenerate braided fusion category. And if in addition the fusion category is spherical, then its center is modular. Okay. So what about the Drinfeld center of pointed and Lagrangian subcategory? This is the following theorem, which will be restated later in something more precise. So a non-degenerate braided fusion category D is braided equivalent to the center of some pointed fusion category if and only if it contains a Lagrangian subcategory. So containing a Lagrangian subcategory for a braided fusion category is the same as to be the Drinfeld center of a pointed. So it's a complete characterization of the Drinfeld center of the non-degenerate braided fusion category coming as the Drinfeld center of pointed. Yeah. Non-degenerate braided fusion category. No, non-degenerate braided. I said just braided. No, non-degenerate braided is the center of pointed if only if it contains a Lagrangian subcategory. A non-degenerate braided fusion category D is braided equivalent to the center of some pointed fusion category if and only if D contains a Lagrangian subcategory. And this make me think about what do you have something more general which you don't assume non-degenerate? Because Lagrangian, you don't need to assume, yeah, you have a braided fusion category, Lagrangian. So if here in this definition, you are saying that in this case, so if you assume non-degenerate here, this is equivalent to B of this form, Unfeld center avec J omega. If you don't assume degenerate, what do you have? I don't know. If there is this can be extended. Let me write it as a question. What if you do not assume non-degeneracy? Can theorem be yeah, anyway. Of course, you cannot expect that the existence of a Lagrangian subcategory imply non-degenerate because a symmetric fusion category itself is contained Lagrangian as itself. Yeah, anyway. Let me see what was Tanakian here. Remark. If Tanakian, then E included in E is Lagrangian. Okay. But anyway, can we generalize? Can we provide a more general characterization of this kind of thing? Okay, 2 minutes. So let me write. So in fact, we will state and prove something, a more precise version of this theorem. And by more precise, I mean involving two categories. We will state and prove a more precise version theorem for 66 involving two categories, two equivalents of two categories. But before that, in fact, tomorrow, in fact, you can see one way of this theorem out of without the precise version in two categories. Just you can prove one way directly by the following remark we will talk about tomorrow. First, observe that the only if part of theorem 464 follow immediately from the next remark. Tomorrow, we will see this remark. In fact, this remark is saying that so. In fact, in general, if you start from a fusion category, you take the Dirichlet center, you have the forgetful functor. You call it pi. And then you consider the inverse of vec. Vec is a subcategory of C, and you apply the inverse of pi to vec. So it's not the right adjoint of the forgetful functor, just you have a functor as a map, and you apply the inverse map in some sense. So and you get a subcategory, a fusion subcategory of the Dirichlet center. And in fact, you can see as an exercise that for any fusion category, this inverse of vec is always a Tanakian subcategory of the Dirichlet center. And if, moreover, C is pointed, then this Tanakian category is related to the group of simple object, something like that. So we will see that tomorrow. So see you tomorrow. Ah.